Welcome to Introduction to Limits, Part 2. In this segment, we're going to examine some examples using graphs and areas of graphs. So the first one is something we did earlier in the year. It's called the Polygon Area example here. We have a regular polygon inscribed in a circle. So we have this subdivided into 8 congruent triangles. The area of a triangle, you may remember from trig, if we have 2 sides and an included angle, we say that area is equal to 1/2 AB sine of C. In this case, it's going to be 1/2 times 10. A and B are both 10 here. 10 times 10 times sine of whatever theta is. So that's where we get this little section in here in the chart. The number in front is just the number of triangles. So there's 8 triangles. This is the area of one of the triangles because that's a 45-degree angle to start with. And if we compute the area, we get 282.84. If we then increase the number of sides so that there are 10 sides to the polygon and 10 triangles, then each angle would only be 36 degrees and we'd have 10 triangles. So this changes to 36, that changes to 10, and we get this area, a little bit more. And then as we increase the number of sides, notice that the area is increasing, but it doesn't increase the same amount each time. As a matter of fact, when we go from 50 to 100 triangles, it doesn't really increase that much at all, just barely. In general, we can say that with n triangles, each of the angles would be 360 divided by n. So we would have 50 as the 1/2 times 10 times 10, which is common to all of these. So 50 times n times sine of 360 divided by n. What happens as n goes to infinity? Well, we're going to look at a little something online that has a picture of this. So here's our circle. It has an area. There's our circle. We're trying to estimate the area of the circle by inscribing a regular polygon. Obviously, a triangle doesn't work terribly well. You see that we know this area of the circle is pi r squared. In this case, this is a circle of radius 1. So it's just going to be pi times 1 squared, or pi. So right up here we have a line pi, which represents the area of the circle. Then this dot represents the area of the inscribed figure, in this case a triangle. As we increase the number of sides, notice that we increase the area of the inscribed figure. So now we're up to 5 sides, 6 sides, 7 sides. So notice the area is approaching the true area of the circle, and that makes sense because each time we add sides to the polygon, the little leftover area in the gray around here is less and less. So now we have, I'm not sure how many sides we're up to, 8, 9 sides maybe. So we'll increase our number of sides. So each time we increase our number of sides, we're getting closer and closer to the true area of the circle. I think this goes up to 20 sides altogether. So now we have 20 sides, and when we get to 20 sides, notice that the area of the inscribed polygon, the 20-sided figure, is nearly the area of the circle. So the question is, what happens if the number of sides of the polygon becomes infinite? With an infinite number of sides of the polygon becomes the circle, and the area becomes exactly pi. I'm going to move that back for my next demonstration. Here you notice that we have a radius of 10, so we expect the area to be 100 pi, 10 squared times pi, or 100 pi. So what we say is the limit as n goes to infinity, n being the number of sides of the polygon, of 50n times sine of 360 degrees over n equals 100 pi, or 314.159, etc. So you can see we're approaching that number, not there yet. I forget how many sides it took, maybe 1,000 sides before we got it to round off to exactly that number. So this is another example of a limit. As something goes to infinity, or we can think of it as the sides of these triangles, the edges of this polygon become increasingly smaller, then we reach the area of the circle. This one is just kind of a simple example to illustrate that when we go to infinity, sometimes we have to consider whether we're going to positive infinity or negative infinity. So we're going to say the limit as x goes to positive infinity of this function, which is 2e to the x. So what's happening? As we go to positive infinity, what's happening to y? Well, y is just going straight up like this. In fact, y is also going to positive infinity. What happens as x is going to negative infinity? So what happens to the function? Oops, that's not supposed to be down there. It's supposed to be up here. Okay. So as x is going to negative infinity, notice what's happening to y. Y is not going to negative infinity. Y is getting close to 0. So in one case we have a limit. It gets to 0. In the other case we don't have a limit. It is unlimited. It's going to positive infinity. So we have a limit on one side but not on the other. Now let's look at something a little bit more directly related to calculus. One of the things you do in calculus is to find an area under a curve. And you might think, well, why would you want to do that? Actually, the area under a curve can be used to represent all kinds of mathematical quantities in problem-solving situations. It's not just a, let's find the area of an odd-shaped piece of carpet or something like that. The area under the curve represents any time you multiply two quantities together, because one quantity can be represented as the base and the other quantity can be represented as the height of something, and sometimes one of those quantities is not constant. It varies, like this function varies. So when we are multiplying a function, a variable quantity times an invariable quantity, this area under the curve becomes a very useful tool. But let's just look at it geometrically right now. So I'm specifically saying, we're looking at this function here, f of x is equal to x cubed minus 12x squared plus 20x plus 336. And that is this function here, f of x. That is the curve that we're looking at. I'm going to go from 0 to 10 in the x direction, so we'll have that be 10. The 0 to 500 just represents the window setting I used to remind myself when I went to this applet online that that's the window settings I used. But you should know what the y-intercept of this function is, because we just had the polynomials. You put 0 in for x, and oh yes, 336. So we know that that's 336 right there. So it kind of gives you a little bit of size. Now if I said, find the area under the curve, what would you do? And you might pause a minute to think about that. Most students think, well, maybe I could divide up this curve shape into, subdivide it into shapes that I can find the area of, like triangles or circles or rectangles or anything else, any other shapes that would fit inside this. And that's exactly right. That is what you would do. I want to start out by saying, what if we divided it into rectangles? And I'm going to start with just 4 rectangles, which isn't a terribly good approximation, but I want to build up an idea here. So I'm going to say that this would be 5, this is 7.5, this is 2.5, and I'm going to draw a rectangle. Now, how should I draw my rectangle? I could do one of two things. Actually, I could do 3 different things. I could draw a rectangle just across from my right-hand side here, or I could draw a rectangle across from my left-hand side here. The other thing I could do is put the midpoint of the rectangle on the function. But I'm just going to use a right-hand rectangle right now, and I'll show you that whichever one you use, you're going to get some area. You're going to get some error. So I'm going to draw a rectangle going from the right-hand side of this function, of this height, the right-hand side of this rectangle, and the right-hand side of this one. Now notice here, when I draw the rectangles, I'm going to shade these in for you, that some of the rectangles give you a bigger area than the actual curve, and some of them give you a smaller. So rectangle number 1 gives you too much area because it includes this little space here. Rectangle 2 gives you too little area because it includes that little space. It excludes that space. Rectangle 3 gives you too little, and then rectangle 4 gives you a little bit too much. But you notice that in 2 of the rectangles, we end up having extra space. In 2 of the rectangles, we end up having extra rectangle. And it sort of balances out. If we added up all of those areas, we should get pretty close to the area of the curve. It looks like it'll be maybe a little too small, but it's going to be pretty close. Now, if I wanted to add these up, I need to know a base and a height for each of my rectangles. The base for each rectangle, it turns out, is 2.5. But the height then, excuse me, the height would be these right-hand sides of the rectangles here, each of those. And how do we calculate those? Well, either you think it's obvious or you have no clue. And if you have no clue, you'll be very disappointed to realize how obvious it was when you do find out. We do know the area of this curve. We know the x value. So if we want to find how high this rectangle is, we just plug the x value into the function to figure out the height here. So this basically, if this is 2.5 down here, over here, the height of this rectangle is f of 2.5. Okay, so I would just multiply each of these x values times the corresponding y value from the function to get the area, the total area of the rectangle. So we could write this as a sum, the sum as n goes from 1 to 4 of x sub n times f of x sub n. That would be a way of writing it, and that gives us our approximate area. Now, if I wanted a better approximation, what could I do? Very good. I'm sure some of you thought of this idea. Make the rectangles smaller. Draw more rectangles. Because if I could divide this into 2 rectangles, think about that. This little area under here, I could get more closely approximated. So I have something online I want to show you that starts out looking like what we have here. And I can add more rectangles. And I want to show you what happens when I add more rectangles. So I've got 4 right now. Let's add 6. Okay. So when you add 6, notice that get a little bit better approximation, but we still have a lot up here. This curve isn't exactly like my curve. It's kind of close. I tried to make one look as close as I could. Let's try 10. Okay, now notice with 10, we see that the extra rectangle both above and below the line has lessened. So let's make it 20. Ooh, now we're getting a really good. The top edges of these rectangles look more and more like the actual curve. Let's try 50. Ooh, that's really impressive. Now let's try 100. Wow. If we go to that extent, we almost have the exact area. Now, imagine going to an infinite area, and I can't do an infinite area in here, but let me show you what 1,000 looks like. 1,000 pretty much looks like the curve, the area under the curve. So if we were to increase those numbers of rectangles to an infinite number of rectangles, we would get the area under the curve. So I'm going to go back to my original one to set it back for later. So as we increase the number of rectangles, we would get a better and better approximation of the area. Another way of saying that is that we could decrease the base, because when we increase the number of rectangles, this base, this distance between the x values, is going to get smaller and smaller. And I'm going to call this little distance delta x, which means the change in x. So as the number of rectangles goes to infinity, delta x gets closer and closer to 0. So basically what's happening is we're going to create a bunch of rectangles whose base is closer and closer to 0 and whose height equals the height of the function. And as that little value delta x goes to 0, that sum is going to get bigger and bigger and bigger. I'm sorry, that sum is going to get closer and closer to the actual area of the curve, the area under the curve. So that's a little bit of calculus here, so I'm just going to say as delta x goes to 0, the area or the sum of the area of the rectangles equals the area under the curve. Now I'm not going to use any formal limit notation here because I don't want to mess it up by making it not look like what you're going to see next year. But I just want to get you the idea. This is the integral in calculus. The integral is the area under the curve, and the integral takes that small value delta x and shrinks it down to 0. It takes a limit as this delta x goes to 0, and we get, and I guess I could say that the limit as delta x goes to 0 of the sum of the rectangles equals the area under the curve. All right, that ends segment number 2 of Introduction to Limits. We're going to look at rational functions and limits in our next segment.